Hello and welcome to an introduction into statistical methods and considerations in randomized controlled trials. This is a tutorial that aims at making you familiar with the most common concepts and terms related to the statistical treatment, the management of data in randomized controlled trials. Before we kick off, let's just say hi to the elephant in the room, which is that it says statistics on this slide and on the tin of this tutorial. Trust me, I wouldn't have thought that I'd be giving a tutorial on statistical considerations of any form a few years ago. So I'm by no means a maths aficionado, and I'm really going to try and introduce you to the principles and key ideas rather than going into details of individual statistical tests. That's not really what this is about. This is about making you able to read the entirety of a randomized controlled trial report, including the stats section in the methods, and also to be able to distinguish good practice from not so good or maybe slightly fiddled with and modified practice in analyzing and then reporting analyses of randomized controlled trials. So with no further ado, let's get going. I'm David. I'm a senior research fellow at the University College of Osteopathy in London and also a research associate at Imperial College. A randomized controlled trial is a scientific experiment, and this experiment usually investigates the effects of a treatment. In our case, we're mainly going to be looking at studies that test an osteopathic treatment and compare it against something else. What you can see here is a flow chart, so a graphical representation of what happens to participants in a clinical study. And that already shows us two fundamental features of the randomized controlled trial. The R in the red circle refers to randomization, and that means that eligible participants are randomly allocated to two or more study arms. And that already is the second distinguishing and important feature of a randomized controlled trial, the fact that participants are either allocated to a treatment group or to another control intervention, control arm, control condition. That can be of different natures depending on the research question, but the essential feature is that you're comparing treatment against something else. And that's because we need to control for things like natural fluctuations in symptoms, which occur irrespectively of treatments. And if you're looking at a placebo-controlled intervention in particular, you also want to control for the contextual factors of treatment that might elicit expectation and placebo effects. So these two features, randomization and a control arm of some sort, are also the main distinguishing features between RCTs and what's called observational and cohort studies. In these studies, you usually have individual groups of patients that are followed up longitudinally, so that are followed over time. And there's no random allocation, there's usually no comparator and no control group either. Now, why do we care about stats? I mean, an RCT, as most scientific experiments, collects data. Yeah, you're asking participants in this flowchart, for example, in this trial, repeatedly how they're doing. You're doing that at the baseline assessment to establish how they're doing at get-go, and then in this study, probably throughout these visits, and in particular at the end of the treatment period and 4 to 6 weeks after the last treatment at what is called a follow-up assessment. So you're collecting tons and tons of data, and then these data are analyzed to identify a treatment effect over the control intervention. Yeah? So you're comparing changes in the treatment arm against changes in the comparator. There are lots of ways in which how you do that can significantly, well, can fundamentally influence your findings. The most obvious example for is if you only look at one treatment, one arm. For example, you compare the baseline values of the treatment group against the follow-up values of the treatment group. So for some reason, you're looking at a within group comparison that basically does away with an important feature of randomized controlled trials, which is the control arm, as we've just discussed. So whilst that on the surface of things looks like a valid and certainly statistically okay thing to do, it undermines the principles of a randomized controlled trial. So that's an obvious example of how selectively choosing parts of your data and reporting that can tell us something entirely different to when you do what you're actually supposed to do in best practice when analyzing and reporting randomized controlled trials. Sounds like a slightly outlandish example, but I assure you it really is not. Yeah, and there are lots more nuances and other ways of changing your stats in order to deliberately or maybe not deliberately find different things. So other important ways of how results change depending on your analysis and ways at which we're going to look in much more detail later on are, for example, who you include in the main analysis. The example that I just gave you refers to that, but also you could think of a situation where only participants who, say, attended most of your treatment sessions are included in your main analysis. That's in contrast to including everyone who was randomized irrespectively of how much they complied with what you intended them to do as part of the treatment. Then there's the issue of what we call the power, so study power or statistical power. That basically asks whether we can be certain that we collect enough data for the results to be able to show with relative certainty or with relatively high probability a certain effect that we're interested in. Don't worry, we're going to look at that in more detail, but the principle is that an underpowered study is a study that does not have enough participants to be able to detect a treatment effect with a given level of certainty. Now, we're always going to lose data, so we might have participants who don't show up for particular appointments, or we might have the situation that we have a technical error, or we can't read the handwriting of the person who was taking the assessment, etc. So if you imagine you're going through dozens or hundreds of participants and individual appointments and outcome assessments, there will be undoubtedly missing data. How you deal with that in your statistical analyses, from whether you ignore that to whether you make the data up, that can very obviously lead to different results. Then there's the issue of what we call multiplicity. So how many tests do you conduct? How many statistical tests do you run? As we'll learn later, the more you test, the more likely you get something, and the more likely you are to find something. And then there are obviously different statistical tests. You will probably remember some of that from your undergraduate training. That often depends on the type of data. Maybe you remember the distinction between categorical data, so data that comes in categories like male, female, non-binary, if you like, or continuous data, for example, pain ratings on a scale. So things that can be divided and divided and further divided. For these, you need different types of statistical tests. You don't have to remember them by heart. And there are only a few really relevant to the analysis of clinical trials. But you should be able to say, well, this is a bit of a weird test. I'm going to look up whether that is appropriate. Then related to data, but also related, and there's always this overlap to general methods of the trial, is the question of what's your primary outcome measure? What's the main thing you want to measure? And then test that in your statistical analyses. So an example here of how the same thing that you measure can be modified, or the data that results from that is, if you take pain ratings, you could say you're comparing average ratings of a visual analog scale, so 0 to 10 of pain ratings, comparing improvements in the treatment arm to improvements or lack thereof in the control intervention arm. So that's one way of dealing with that continuous data. You could also say, well, I'm really interested in what's the percentage of people who get at least a 3-point improvement. So you suddenly put people into categories, you've changed your data, or you're looking at proportions, and suddenly you're asking a different question with the same data. Yeah? And exactly because there are so many different ways of influencing what we find with an RCT, it would be essential for study authors to very clearly define before collecting or looking at their data what they intend to do in their statistical analysis. So the onus really is on the study authors. And for that reason, authors shouldn't just register a protocol in which they say what they're generally going to do in that trial, but they should also pre-register what we call a statistical analysis plan, or SAP. As you see in your own work, but also throughout this, that's not particularly common. And there's a lot of detail that would be requested and necessary, and it's only in a few journals where that really is reinforced. So that's my introduction into the topic. Yeah, we're going to go through about 8 to 10 themes and topics that you're going to encounter when reading a randomized controlled trial report. That goes from the first table, the descriptive or demographics table, which reports what people looked like and reported at baseline, all the way to how then study authors analyze their data and how they interpret these analyses. So even if you run the right analyses, you could still put some spin on how you represent them in your writing and what you focus on. So let's kick off with the descriptive statistics. So that's about who are the people that were included in this scientific experiment in the randomized controlled trial. What we're really interested in are summary statistics for each arm of the randomized controlled trial. And you want to know that before presenting any results. That's important for 2 reasons. First, that the reader knows who the participants were, on which the treatments were tested, and to which or to whom the results apply. So really the who question. Yeah. What we want to know there is not just how did they look or what did they report on average. And that includes things like what's their weight, what was their health status, were their baseline symptoms, but also how much did that vary within the group. Yeah, it makes a big difference whether or it's a different group of people if you have an average pain score of 3 out of 10, but most people are within sort of 2 and 4, or if you have an average of 3, still the same, but you have quite a few people with no pain at all and quite a few people with a 6, 7, 8 out of 10. So that's what we mean by spread or variance. So it doesn't suffice to report the mean or median, which give you sort of the mid values, but you also need to give a measure of variance, which represents the spread around this average or median value. And secondly, by presenting descriptive data, such as age, sex distribution, BMI, or baseline pain, and other clinical levels, we can check whether these 2 groups that we're looking at were actually similar at baseline for any kind of variable that might be linked to outcomes. So if for some reason you have way more people of one gender in one of the groups, then you might be wondering whether that randomization process that people should have undergone was actually efficient and worked out. Because if you randomly allocate people, by chance you should have relatively balanced main features and characteristics. Why is that important? Well, if you're testing the effects of exercise and one group, for example, has significantly higher baseline pain levels or lower baseline physical activity levels, that might influence the results because they may be less engaged in your treatment, or they might start on average from different starting points. And randomization should balance these baseline characteristics out. Yeah. So by presenting those, that allows you as a reader to objectively compare baseline characteristics between the two arms. These are the two main things you want to be looking at in the descriptive part of the results section, or in that famous first table of randomized controlled trial reports. And the way you can compare those two groups is either by visual inspection, so how much did the mean values differ from one another between the two groups, or sometimes authors report t-tests, so comparisons for statistically significant differences between those two groups, and you can use these results to estimate whether they were the same or relatively similar in characteristics. Now we're getting already to the meat of the issue. Hypothesis testing is really what you want to do with the data that you've collected in an RCT. In the context of an RCT, hypothesis testing is a statistical process used to assess whether there's a significant difference between treatment groups or conditions. Yeah? It involves comparing observed data from the trial to what's called a null hypothesis. A null hypothesis represents the assumption that there's no real effect or difference between groups. That's at first a little bit counterintuitive, but really this is about creating a scenario of probabilities against which you can then check the data that you've collected. So the null hypothesis typically states that any observed differences are due to random chance or sampling variability. In other words, hypothesis testing in an RCT is essential for determining the efficacy of treatments, and it helps researchers to make informed decisions about whether the differences that they've observed or the effects that they found are likely due to the treatment itself, or whether they could have occurred by chance. And then next to the null hypothesis, you have the alternative hypothesis, which contradicts the null hypothesis, so it's the opposite. And based on collecting data, determining a statistical significance level of what's called alpha, and that's usually the famous 0.05 p-value and alpha level, choosing a appropriate test for the kind of data that you've collected, you can then calculate a test statistic and compare that against your null hypothesis. Usually, if p is lower, then, hold on, is this correct? Usually if p, yeah, that should be differently here on the slide. One second. There we go. This is the appropriate one now. So if the p-value is lower than your significance level, you can reject the hypothesis, the null hypothesis. In other words, you can say that it's not true, that there's no significant difference between the treatment groups. If p is higher than 0.05, you fail to reject the null hypothesis. This means you can't exclude the possibility that the treatment differences that you found are due to chance. In that case, we say it's statistically non-significant, and we would abstain from drawing any conclusions that would claim any kind of benefit beyond chance. Now, appropriate statistical tests, I've mentioned that before. These really are just names that I want to remind you of. You've heard of t-tests, ANOVAs potentially, so analysis of variance, and regression models. These are all ways of comparing continuous data, either between two groups or between three groups or more. And regression models are very similar, but they are a bit more sophisticated and flexible in what else you can do with them. So it's much easier, for example, to include effect modifiers into your analyses. When you're comparing categorical data, you're looking at chi-square tests, Fisher's exact test, or logistic regression. If you come across a statistical test that isn't listed here or that you don't know about, it's best to go and check for how that is linked to the data, whether that's appropriate or not. Now in the script, you're going to find a little bit more detail about statistical tests. That's something to remind you of your undergrad teaching probably, and also to help you by allowing you to look it up when you need it. Right. The next topic relates to multiple testing. Now imagine you're rolling a die to get a 6. If you roll it once, you might get a 6 by chance. But if you roll it many times, well, the more times you roll it, the die, the higher the chances you get a 6 eventually, even though the die is not rigged. In statistics, this is like doing lots of tests on your data. If you keep trying different tests or run tests on multiple outcome measures or different variations of the same outcome measure, you're more likely to find something that hits that significance level just by luck, not because it's actually likely to be there. And that's called the problem of multiplicity. Researchers therefore need to be careful to test too many things in order to avoid false discoveries. And these false discoveries are called type 1 errors, also called false positive findings. They look like a real finding, could be a 6 or it is a 6, but they are a product of chance because we tested too many times. Yes, it's a 6, but it's a 6 after 10 tries. So in research experiments, if you keep testing hypotheses and don't adjust for the number of tests, so you have to make your level more stringent. We're going to go into that in a second. You might mistakenly declare that you found something significant or a positive result when it's just a result of random chance. This is the risk of making a type 1 error due to multiplicity in statistical testing. Well, what can we do about it? We can address the issue of multiple comparisons. Sometimes you do have to run multiple tests, but the best way of addressing multiple comparisons is avoiding multiple testing. Yeah. So ideally, the way this is done is by declaring beforehand what your primary outcome measure is and what the planned statistical analysis is before you actually collect data, or at least before you start analyzing, really looking at the data. That means that you've committed to what's the most important thing to test in your study. That should be linked to a clinically relevant question, usually in randomized controlled trials, and often, well, always researchers have a good think about why they choose this and not some other test and outcome measure, to align it with their research question, but also with what they think they already know about the treatment or the circumstances that they're studying in. Everything else that you haven't declared a primary outcome measure are additional either secondary tests or exploratory tests. The importance of those you're definitely not supposed to overemphasize in your trial report. I'm going to get back to that later. If you do have to run multiple tests, there are ways of correcting for that in your statistical analyses. You may have heard a beautiful word, Bonferroni. Bonferroni adjustments or corrections basically mean that you make your significance level lower and lower for each test that you run. And similarly, rather than doing that, following that particular method, you can just say, you can pick a lower significance threshold. For example, not 0.05, but 0.01 or even 0.001. If you think of genetical testing, for example, where they look at significance levels of multiple genes and gene variations, multiple, I mean hundreds, if not thousands, you will find that the significance levels there are way lower, and often they use more sophisticated levels, more sophisticated methods of adjusting that. You could also focus on effect sizes, which is a measure of how big the effect is or the differences between the groups that you found. So not just is it statistically significant, so not particularly likely due to chance, but also how big is it. If we look at a population, what's the difference on average, and what does that mean when you translate it into the outcome measure that you're measuring? And often for particular outcomes, for example, pain levels or disability questionnaires or functional tests, people have tried to establish what we call minimal clinically important differences. So that's something that patients and usually practitioners or other stakeholders would consider as worthwhile, worth their time, worth the investment, and not least notable in a way that influences quality, survival, whatever, some kind of higher level outcome that people are generally interested in. Further than that, trial authors should really be transparent about how many tests they've run and what they did. If they need to run multiple tests, or they did it to generate hypotheses or just try something out, they should still disclose what they've done and make clear what of that was pre-specified. So what had they planned to do beforehand, and what did they explore as they saw the data and why. A few other methods that we don't need to go into detail here now. Right, I just want to introduce you to the concept of p-hacking, also known as fishing for significance. That's a questionable research practice in statistical hypothesis testing. It involves manipulating or selectively analyzing data in such a way that it increases the likelihood of obtaining statistically significant results. That's often with the goal of confirming a hypothesis or achieving a desired outcome. Unsurprisingly, p-hacking can lead to misleading results, and it definitely undermines the integrity of scientific research. There are unfortunately some incentives why people would engage in p-hacking or significance level fishing. And that's not least because it's boring to say something doesn't work. There are often vested interests. If you look at drug studies, you can see that from a financial point of view, but also within physical, psychological interventions. Often the people who study the treatment have some sort of at least emotional conflict of interest, or for example, I'm an osteopath. Proving that osteopathy doesn't work isn't maybe not the best thing for my own clinical practice, maybe not even for my reputation as an osteopathic researcher within the community. And it certainly makes it harder to publish clinical trial reports, because unfortunately, and even though that shouldn't be the case, trials that show no differences or no benefit are much less likely to get published. So lots of incentives why people might engage in p-hacking. Still, that doesn't justify and still means we need to look out for it. Basically, p-hacking increases the type 1 error probability, or it makes it more likely that we're actually looking at a false positive result. How can that be done? What are the things you look out for? If people don't report analyses that are actually based on the entire group of people that they've included, that they've recruited. So for some reason they're looking at subsets without a good justification. Some people have used the word trawling rather than fishing, and that really refers to running so many tests, often also collecting so many outcome variables, that you have many options to run tests. A good example are physiological studies. So if you're measuring someone's heart rate variability, there are at least 5-6 different ways of splitting that data into different domains. If you then test or collect the data at 5 different time points, you've already got 5 times 5 possibilities of statistical testing, and then add the differences groups, etc. And suddenly you end up with lots and lots of different tests that you can run. And just by chance, you might find a few of those to be significant. Then you can hone in on those and discuss them and say, well, your treatment changed X, Y, Z little variable, not mentioning that was 3 out of 100 tests that you've run. Often you see big results tables there with some asterisks here and there, and that's what authors report on. You can adjust your analysis methods in a way that's not particularly appropriate. So you could adjust for participants' baseline values, even though there's very little to suggest that they are actually influential from a clinical point of view, but they might make a statistical difference. Whether or not that's practically or clinically relevant is a different question. So even these adjustments need to be justified. Publication bias is what I said about the likelihood of publishing negative findings being so much lower. So it's certainly not always just down to researchers. There are also external incentives that produce, that lead to the situation that positive reports are more likely to get published. Our next topic refers to power and power analyses. And these power analyses are crucial in research because they help us ensure that a study has sufficient sample size to detect meaningful differences or effects, should they exist. So here's the difference for you. Assuming there is a significant difference between groups or significant treatment effect, having sufficient power means that your study is likely to detect these differences if they are there. So this is about optimizing the chances of uncovering something and to avoid false findings. Power is very closely related to the likelihood of making false positive or false negative errors in hypothesis testing. We've spoken about false positives, so the possibility of finding something even though that's likely just due to chance. False negatives are when you have the risk of making of dismissing an effect even though there might be one. So having a negative, statistically negative or significant, non-significant finding, even though in actual fact the treatment would work. If you had a bigger sample, you may have been able to show this treatment. So that's related to having an underpowered study, a study that wasn't large enough to show a particular effect of interest. So how do we go about this? You're defining your hypotheses, your null and your alternative hypothesis, and you're specifying a significance level of the statistical test that you want to use in your main hypothesis testing. So that would be the 0.05 significance level usually. And then you're defining a target effect size and an expected variance. The target effect size is the measure, the difference, the size of the difference between the groups that you're interested in. So you could say, well, anything below 2 out of 10 differences in pain levels is really not clinically significant. It doesn't matter. It wouldn't change clinical practice. It's not worth looking for anything smaller than a 2-point difference between the groups in terms of treatment and symptom improvement. You'd also have to specify how much you expect that effect to vary, or how much variance there will be between the two groups. So how much spread there is between the amongst the study groups. And then you choose your power, and your power means, in this case, the probability of finding an effect should there be one. Yeah, usually we're looking at an 80% power. Some studies are powered to 90% probability, and then you just put that into your into a calculator or into a software usually, and that spits out the number of study participants that you need in each group in order to have sufficient power to show the effect of interest at a particular significance level. In this script, there's an example. It's not particularly complicated, but what's important for you when you read trial reports is, first of all, well, authors should report the statistical power of their sample, and they should ideally report that they've conducted a power analysis beforehand, so that they've run through these scenarios and determined what's the effect size of interest and how many study participants do we need for that. Then they recruit for it. They usually add a few more to make up for participant loss and missing data. And then they can say, well, we've reached our target sample size or we haven't. And the same can be done retrospectively. You could say, well, we've only recruited 100, not the 150 that we wanted to recruit. We can make what's called a post hoc power analysis and say, well, if there's an effect, what's the probability that we found it with this smaller sample size than anticipated? So what they should report is really what the objective was of the power analysis. Was it to determine the sample size, or was it to go through different scenarios? What's the primary outcome that they've actually powered their study towards to? So was it differences in pain levels, or did they look at disability outcomes, etc.? What were the assumptions that they've put into the model? That's what we've just discussed, the software, and then the detailed results. So rather than saying our study was well powered, they should really be able to say we've had X% of power to show Y effect size, etc. Now, I want to come back to the idea of a primary outcome and how that should be presented. A primary outcome is the effect of interest. That's the effect that's most important in a trial, and ideally the outcome measure and analysis for which the trial is powered. That's typically chosen based on the trial's primary research questions or objectives. So this could be, does osteopathy reduce back pain more than physiotherapy? The primary outcome would be back pain, and your primary analysis would be a comparison between the two groups. So this primary outcome serves as the basis for determining the success or the failure of the intervention or the comparison. In contrast, secondary outcomes are not the main targets of interventions. You will find them too, but the study is usually not statistically powered to show effects, so there might be a higher chance of having false negative findings, and also authors should therefore, because of that lack of power usually for secondary outcomes, not overemphasize results of secondary outcomes. So you might have the scenario that primary outcomes, primary analysis wasn't significant, but you found something on the 3 to 10 different secondary outcome measures that you've tested for. You could then choose to say, well, osteopathy doesn't reduce back pain, but for some reason it makes people prettier. Well, that's first of all clinically questionable whether that's as relevant as pain levels. People don't usually go to the osteopath for beauty. Bit of a ridiculous example, I admit. But the main thing is maybe beauty is measured completely differently. Maybe you would have needed a much higher sample to detect any kind of meaningful differences between groups, etc. So you may have the situation that you're just having a higher chance of finding something there or missing an actual effect. So higher levels of type 1 and type 2 errors. Then there are exploratory outcomes. These really are hypothesis generating, so you don't really know how a certain outcome might respond to osteopathy versus physiotherapy. You include it in your study in order to, well, explore, and based on that you might decide, oh, we need another research program to investigate the effects of osteopathy on something. But that trial doesn't give you the answer. It just gives you an indication or an idea or a good reason to further pursue a particular avenue of research. When reading the presentation of primary outcome analyses, this is really what you should be looking out for. You want a clear statement of the main result. Osteopathy does or does not statistically significantly improve back pain compared to physiotherapy. Clear statement, no wiggle room, really. Something like using words like beneficial or maybe have nothing to do in main outcome result statements. You also want to be able to find the underlying data, the means and standard deviations for each group and for the time points that went into this analysis. Ideally, authors not just report statistically significant differences, they also quantify that as an effect size. So how big is that effect? If they are available, and they not always are available, minimal clinically important differences should also be discussed. How statistical analyses were adjusted should be reported, and ideally you have access to the raw or unadjusted data. We're going to go into adjustments or controlling for confounding variables in a second. That will make more sense then. Like I said before, in a randomized controlled trials with multiple participants and multiple outcome assessments, you would always have missing data. That's okay, and it's particularly common when you have trials that stretch on for multiple weeks or multiple appointments, or if you have populations that might struggle, so participants who might struggle to always attend testing assessment appointments, who might not have access to phones where you can call them, etc. Or who might have such fluctuations in symptoms that sometimes they just don't even feel able to report results. You might have that often in depression trials or in dementia studies. You have different challenges linked to the clinical picture that you're looking at. Now, there are various methods of how to deal with missing data, but these methods can fundamentally change your results. Imagine you have 100 participants and you've got 10-15% missing data. So if you simply remove everyone who's not provided a full data set from your analysis, these may be the particularly sick patients, these may be the patients that had some kind of social limitation, weren't able to take phone calls, so you might have just excluded the working population, or you might have excluded the people who are living in the countryside and they had to travel further for your assessment appointments and therefore missed more. So suddenly, by removing them, you've removed a particular type of patient. And that's always an issue because this sort of thing undermines randomization. Remember in the beginning, what we're trying to do is balance out participants. If we suddenly then non-randomly select a few and kick them out, that will undermine randomization and make our groups biased. That makes it more likely for results to be actually due to something that's not the treatment. There are ways of dealing with dropouts and missing data, but they all have certain assumptions. So like I said before, the best way of avoiding having to deal with missing data is avoid having missing data. So collect as many data points as possible, really follow up participants in a stringent manner as much as ethically possible, maybe even incentivize to provide outcome data. There are like I said, statistical methods. Let's go into those. There's a complete case analysis that excludes cases with missing data. Like I said, this is straightforward, but it reduces your sample size and it introduces potential bias if the dropout reasons weren't random. Oh, another good example here, by the way, are side effects. So if you exclude everyone who didn't follow up and people had side effects and then for that reason didn't attend outcome assessment appointments, you can really underestimate treatment effects. So you might have excluded the people who've benefited least and therefore raised the average of how well people are, and that reduces the effect between the difference between the groups, if you see what I mean there. There are imputation methods. That means you're replacing the data that you've lost with something else. There are different ways of doing that. There's last observation carried forward. So the last data point that a particular participant has provided will be carried forward, so will be used to replace all the subsequent missing values. You could do the same, but not with the last observation, but with what they had at baseline. Different assumption again. Completely takes out anything that happened during the treatment period. Or you could say, well, best thing we can do at this point is to assume that data are missing at random and you replace them with random values from within the data set. So logical values, but randomly selected. Then there's what's called the estimate framework. This is an upcoming methodology, really, that rests on a pre-specified and very clearly specified set of assumptions. Often that's linked to dealing with missing data and means that you're collecting reasons for why people were not reporting outcome data or went missing in the trial. And then based on different reasons, you put in different types of values. So you change your imputation methods. So for example, the values of the control arm, so the group opposite, may be used for everyone who drops out because they don't experience any treatment benefits. So you have someone stopping to continue treatment and they say, well, I don't feel any benefit, I'm not doing this anymore, see you later. They won't give you any follow-up data, but you know why they've left, and you probably pretty fairly assume that they did pretty similarly to the control group that didn't receive any treatments. Now there are ways of addressing the problem of missing data is essential to prevent biased results. Like I said before, ideally you do this by collecting comprehensive data. You could also run sensitivity analyses. So in your main analysis model, so your main set of assumptions and statistical test, you may have chosen to use a last observation carried forward method to implement and impute missing values. In your sensitivity analyses afterwards, after you've reported, this is what we found with our main analysis, you could say, well, but we wanted to see how much our results were liable to the statistical assumptions that we made, and you can vary those assumptions. So you could compare that to doing the same analysis but replacing data with random values, etc. That allows you to better understand how robust your findings are. There are other methods, and an important thing to do is also collecting dropout reasons. When reading trial reports, often you might find that missing data handling methods aren't mentioned at all. Like I said, in particular in randomized controlled trials that go on over multiple weeks or have long follow-up periods or complicated treatment regimes, that's an issue because likely they've had missing data and they will have had to deal with it somehow. You want to know why. You want to know how they did this, because like I just told you and like you've just learned, what you put in for your missing data will influence your results. Subgroup analyses are also a way of understanding your results better. For example, you could ask whether patients who attended all appointments had different outcomes than those who didn't. However, subgroup analyses are always another statistical test, so that means you're increasing your type 1 error risk. And they also split the sample according to potentially non-random features. And by doing so, they can be biased. And therefore, conducting and reporting subgroup analyses must reflect such limitations. Ideally, authors should have a good rationale and pre-specify the subgroups that they are interested in. If they don't do that, they become problematic. Good reasons for conducting subgroup analyses are you want to explore the treatment effect variation among subpopulations. So you might be aware that there are subpopulations in your sample. You might have a group of diabetics, and within those there are some with good blood glucose control, and there are others where blood glucose isn't as well controlled. So you could split that into two and say, okay, we found an overall treatment effect. Let's see if that treatment effect was there in both of those groups, or whether actually this treatment is only efficacious for one of those groups. Related to that is the question of clinical relevance. Subgroup analyses may be warranted when there's an a priori clinical or biological rationale, suggesting that certain subgroups might respond differently. So, blood pressure medication, for example, may have varying effects in different age groups or genders due to physiological differences. There are safety considerations. You may identify that, well, everyone who was pregnant in this trial had adverse effects. So you might run a subgroup analysis not on treatment effects, but on adverse effects. This information is crucial for ensuring a treatment safety profile across different groups, or ideally, or maybe informing further research. You can also use subgroup analyses to investigate what the reason is that some people benefited and some people didn't, or some people benefited a lot and others only a little. Is there something that you didn't know before, which is worth further investigating, to suggest that your treatment only works in particular, based on particular patient characteristics? But like I said before, subgroup analyses should really be approached with caution. You should have an a priori hypothesis. You ideally have enough power. Like I said, studies are usually powered to show an effect on the main analysis and main outcome. If you split your sample into subgroups, you're usually not powered to show effects anymore. Subgroups should also be independent, so there shouldn't be overlap between the subgroups, so people should be in two subgroups and inform multiple analyses. Should be clinically interpretable and relevant. It's an interesting thing often again in biomechanics studies. They find something and they say that, well, this treatment improved shoulder health in general, but actually what they found is that it improves on average lateral rotation a little bit, or statistically significantly, but whether that actually links to any kind of functionally important or clinically important values is not always clear. And if you then apply the same principle to subgroups, you've got the same situation here. And again, we need to know, was that something that was planned, or did people explore this and run multiple subgroup analyses, use multiple covariates to split the sample in, increasing the chance of finding something just by chance. Related to subgroups are so-called confounders or covariates. These are factors that influence trial results That means they are statistically associated with the outcome of interest. You're testing, let's say, pelvic pains. So the outcome of interest is the occurrence of, say, monthly pelvic pains. Unsurprisingly, the variable sex may be statistically associated with that outcome of interest, so it might confound your results. If we want to study the prevalence of pelvic pain irrespective of the participant's sex, we might consider sex as a confounding variable that we want to control for in our experiment. One way, non-statistical, of doing that is to exclude participants with that confounding variable from our study. In other words, you're only recruiting biological males in studying pelvic pain in them. You can see that's a slightly different clinical question. Another way is a statistical adjustment that controls for the effect of pelvic pain being more prevalent in biologically female participants. But there are less obvious examples than this. Basically, you're looking at certain occupations, physical, mental characteristics, leisure habits, comorbidities, medication use, etc., that may be associated with better or worse responses to treatment. If we identified such covariates and we are not interested in them, so we don't want to run a subgroup analysis, we may want to control for them in our statistical analysis as so-called confounding variables. So we want to cancel out the effect that they have and say, irrespectively of, for example, sex, people did or did not improve. Identifying covariates can be done either prospectively, so you might know that there are certain covariates. Good example is, again, from sort of physiological literature. If you're measuring blood pressure or heart rate variability, we know that caffeine consumption, coffee drinking, can influence that. If we're not interested in that, or if you want to avoid that, you could encourage participants to not drink coffee a few hours before your study or on the day of assessments. Or you could say you're correcting your analyses for the amount of coffees people drank. So you could also, that would probably be a regression or other adjusted statistical method that I've just explained to you. You could also stratify. So that's subgrouping based on potential confounders. A good example are study sites. So if you run a multi-center study where treatments are delivered in multiple treatment centers, you may have some treatment centers that are academic hospitals, highly skilled surgeons and super good equipment, and you may have some that are only maybe even understaffed and disadvantaged. So you could say you want to know what the difference is or what the treatment is, irrespectively of how well equipped and staffed hospitals are, and you could therefore stratify by study site. That might show you that it does or does not have an influence on outcomes. There are some other ways that you'll read about in the script, but that's, I think, enough for the question of covariates and confounders. I've touched on context sensitivity analyses before. They're really a good thing, one has to say. They show that study authors were critical and interested in really demonstrating, looking at their results from different angles to show how robust their results were. How much do they hold up under different varying assumptions? I've given you the example of testing our missing assumption, our missing data assumptions, but they are also a good way of quantifying the influence of covariates on results. So not excluding covariates, but to check whether these covariates were actually in your analysis influential and had an effect on the results. You may have the situation that there are some people who responded extraordinarily well or poorly. These are so-called outliers. Usually you don't exclude them from your analysis, but maybe to increase the robustness and your trust in the findings, you want to exclude them for some sensitivity analyses, which might show you that, yes, actually, that significant effect that you found was mainly due because 3 out of 50 people responded super well. Or it might show you, no, even without those surprise patients, we did find a significant or maybe even clinically important difference. You can have various practical concerns, considerations, limitations of your study. You may have found that there's a high level of non-compliance, and maybe a sensitivity analysis is a good way of checking whether the extent to which people complied with your treatment plan actually was influential. The question of what you do with people who don't comply with your treatment plan leads us to the next topic, which is what we call the analysis population. So who are the people that feed into your main analysis? There are two important approaches to distinguish. One is what we call the intention to treat analysis, and the other is the per protocol analysis. There are also modified intention to treat analyses, but I don't want to introduce those to you here. In a normal intention to treat analysis, all participants are included in the analysis as they are initially assigned to study interventions. That preserves the randomized nature of the trial. That's irrespective of how much of the study intervention they completed or whether they attended any treatment sessions at all. ITT analyses can arguably prevent bias, and they do reflect real-world circumstances. So in clinical practice, even though your plan might be to have 6 appointments with all your patients, not all of them are likely to actually attend all of those 6 treatments for various reasons. If you're thinking of home exercise programs, etc., you can also see how non-compliance, but still including people in the analysis, may be more akin to real-world circumstances than excluding them simply because they haven't followed your treatment plan or your home exercise plan 30 days a month. Per protocol analyses, on the other hand, exclude people who don't adhere strictly to the study protocol. That might be appropriate under certain circumstances, in particular when your question is not, would this work in normal clinical practice, but when your question is, does this work under ideal circumstances? So, assuming that everyone really does what we tell them to do people get better? Or assuming that people really take the medication that we want to test here, would that be useful? However, excluding anyone from the study might risk selection bias, so you might exclude, like I said before, the sicker patients, the patients with high disability levels, the people with certain preferences or certain characteristics that might actually make them more or less likely to respond, and thereby you're undermining randomization and you're biasing your findings. Per protocol analyses also reduce generalizability referring to the applicability of findings outside of your trial circumstances. So that's the opposite of being highly real-world relevant. It means, well, that's really a finding that only applies to the specific circumstances and assumptions of this RCT. Either way, the analysis population must be pre-specified. It's a really good example for how changing the data and what you do with your data will influence drastically, potentially, what you find and what your conclusions are from your RCT. Good. We're nearing the end of our tutorial. I wanted to introduce you to one special case only because it's really common, and that's what we call the crossover design. This is a lovely image here. What it shows is that after randomizing patients, 189 in this case, people are allocated, people receive one of two treatments. That's your normal randomized two-arm controlled trial. They finish that treatment course, and then occurs a crossover. So people who got, in this case, MGI, then go over to the other side and receive HGI for the next treatment phase, and vice versa. In between, you've got a washout phase. That means you're waiting for a certain period of time to ensure that any effects that your treatment had in this first period is no longer influencing your participants, no longer present. So you're hoping to start from scratch and use the same participants, give them the opposite treatment, that might also be a placebo-controlled treatment, and then analyze them again. You then put them all into the treatment analysis, apart from this one bugger here who didn't eat rice. I honestly don't know what the study was that I took this graph from, but how can you not eat rice? Anyway, what you're doing with this is you're hoping to increase your sample size, basically, because you're testing both treatments on everyone, rather than splitting your sample in the middle and testing one treatment on each group. But that comes with a few issues and challenges. The main is the clinical possibility of doing this. In this scenario, 1 week washout was apparently enough to have gotten rid of any physiological effects that this treatment had on whatever they were measuring in these participants. If you're thinking of an exercise intervention, you're giving people a new exercise protocol to try for 6 weeks. And after that time, you're saying, well, now we're stopping this. Now you're on the lazy couch potato regime, and you're doing 6 weeks of watching all your favorite Netflix episodes. You might have the issue that some people carry over their newly found habits and continue doing exercises. Or the other way around, people who've first been in the couch potato phase may have gotten so used to it, or may now be so motivated that they do something different to when they, compared to if they just had one treatment, not the other. So that's a carryover effect that you, in some scenarios, can't account for. Another important thing is that the clinical problem that you're looking at ideally is chronic and long-lasting and doesn't get better on the long run. So with exercise, for example, if you have a long-term benefit, whether you have that or not, maybe on back pain, for example, maybe that's not a scenario where a crossover trial is indicated, because people might have benefits 6 months down the line, 12 months down the line. You can't wait that long to crossover. The washout period is the time that you want to wait to avoid those carryover effects. There are analysis challenges. They crossover data usually require specialized statistical tests, but often you might find them not appropriately analyzed. Why do you need specific tests? Well, you have correlations within those subjects. These groups aren't independent anymore. Usually you can use an independent sample t-test, which assumes that groups are actually doing something different. Suddenly you have more links between individual treatment periods because you're using the same participants. That needs to be accounted for. Order effects is what I referred to initially. Does it matter whether you receive MGI first or HGI first on what you then do after the crossover? Sample size considerations. And then finally, how you present those data. What you're going to find is that often they lump these data back together, and you can't even identify how the group MGI versus HGI was after the first phase, whether they returned to their baseline values, and whether that was different after that second treatment phase, treatment period. Right. Talking of how you present results, let's look at data visualization with figures and graphs. So here's a figure. Pain relief per group. People in the active treatment are shown in blue, and you can see the value at baseline and at follow-up, and you compare that to the orange group, which was somewhere on, which started off from a similar point, and then clearly improved less, right? You would say at follow-up, FU here, you've got quite a difference on visual inspection. Now let me put the same graph next to it, but this time I've added what we call error bars. So I've indicated to you now visually how big the spread, the variance around these mean values was. And you can see that at follow-up, these confidence intervals or standard deviations, whatever the measure here might be, are overlapping. Overlapping confidence intervals usually mean there's no statistically significant difference between groups. So on visual inspection, again, already this effect doesn't look as promising anymore. If I then do something else to this graph, oh, what happened here? Suddenly, pretty boring, not something I'd pay money for. And the only thing I've changed is the y-axis, the vertical axis on the left, is now not going from 3 to 4.5 on what you now know to be a 0 to 10 scale. So yes, this looked big, but actually we're looking at a 1-point difference in a group that started from with a 0.1 difference in the beginning. Yeah, not a lot of improvement, no statistically significant difference between them, certainly not clinically relevant. The y-axis is a really fun thing to look out for in visual representations of trial results. Often meddled with, should usually really represent the actual scaling of the outcome domain, outcome measure that you're looking at. So here are a few features, best practice ways of doing your graphs, showing graphs and annotating graphs. I'm not going to go through them in detail, but really a figure should be able to stand alone, ideally with its caption, and accurately, without any kind of trickery, represent what the data were like, how it was distributed, and whether or not what you're visually representing is aligned with your hypothesis testing. What you often find are figures that overdo it, so put in tons of things, put in individual data points, put in multiple outcome assessment, multiple groups, lots of significance testing and asterisks, etc. And eventually you're not able to distinguish anything anymore. So simplicity and clarity, also guiding principles, hopefully. Right, it's one thing what you do in your analyses. It's a completely different issue how you report that. There are guidelines that indicate what trial authors should put into their manuscripts, into their reports. And these are called the consolidated standards of reporting trials, the consort statements. The basic one currently in place is Consort 2010. There are lots of so-called extensions of consort statements for specific types of studies, and that includes one extension for non-pharmacological RCTs. So you can look that up as well in the references. If we look at the consort checklist. So this is the minimum amount of stuff that people should be reporting for their RCT. I've highlighted here all the things that authors should report with regards to their data and their statistical methods. What were the methods used to compare groups for primary and for secondary outcomes? Which additional analyses were they used? Subgroup analyses, adjusted analyses, sensitivity analyses. For your baseline data, include this table, show characteristics for each group. For each group, you want to know the number of people included in each analysis and whether the analysis was by original assigned groups. So whether we're looking at an ITT analysis or whether something influenced whether people were included in the analysis or not. For each primary and secondary outcome, present the results for each group. Present the data, the estimated effect size, and its precision. So how confident can you be around this group difference that you may or may not have encountered? Any additional analyses, distinguishing pre-specified from exploratory. Second part of the, oh no, I've skipped this one. First part, this is, of the consort checklist. Your outcomes in the methods section here should be pre-specified, primary, secondary outcome measures, how, when these were assessed, so how the data were collected for this, but also how sample size was determined. All of these things you'll be glad to recognize now, I hope, we have discussed in this tutorial, and you should be able to at least understand what's meant by those. After the study authors have reported and written up their statement, or their manuscript, you'll be reading it. I'm doing too many things at the same time. As we've seen, there are tons of ways in which the treatment of RCT data can vary, and thus how results can be influenced. That might influence what authors can report. So when reading the results and the discussion sections of a paper, but also the abstract, you want to identify if the author's conclusions are actually aligned with their statistical testing and whether their conclusions are appropriate in light of the underlying assumptions and limitations of their tests that they did. So what I'm presenting here is a minimum list of things to look out for. Are their conclusions in line with the hypotheses? Are they actually concluding based on what they wanted to test and what they did test for their primary outcome measures? How does this link to statistical and clinical significance? What you often find are, unfortunately often actually, are sentences such as, this study suggests that osteopathy may help with back pain, and what they are referring to is treatment is within group differences. So people improve with osteopathy, or what they don't say is that people without osteopathy also improve, and there's actually no difference between the groups. Power, was the study large enough to, with high confidence, show an important effect? Do they focus, that's an important one here, on the primary outcome and on the analysis that they declare to be the most important one? If they haven't declared any of that, you've got your first problem. Where they're missing data, is it likely that missing data were there if they haven't mentioned it? So how many people, for example, dropped out in the study? They should really be reporting, the authors should be reporting what they did to replace these missing data. Subgroup analyses, sensitivity analyses, generally, like I said, a good thing. Have they done any? Should they have done any? If they've chosen a particular set of assumptions for their analyses, did they test that? Sometimes you have to look at the supplementary material for that. data visualization, reporting compliance with consort and relevant consort extensions, and then alignment of conclusions with what they've actually found. There are other things you want to look out for that aren't necessarily directly linked to statistical methods. That includes other risks to the internal validity of results. So we're talking about bias. That could be issues to do with blinding of participants, or it might be challenges inherent in clinical trial design. There is the question of external validity and generalizability. So how applicable are trial results to other settings other than that of that RCT? Again, not really discussed here. And then finally, the issue of spin in the interpretation, where authors may overly emphasize positive outcomes, downplay or not mention negative findings, or present their results in some other misleadingly positive light. You can again especially look at the abstract here, discussion and conclusion sections. So in conclusion, this tutorial should have introduced the main concepts in terms of main conclusions and terms relevant to the understanding of statistical methods used and reported in RCTs. It's important to know that statistical methods are not the only important consideration in randomized controlled trials. Design methods are also important, as well as the integrity of the researcher and their compliance with best practice. But I think what we can be certain of here is that there is a need to look critically at randomized controlled trials and how they're reported. Statistical methods remain a main source of confusion for readers, so it's easy to skip that. But as you know now, statistical methods also provide lots of opportunity to knead the data in a way that shows what you hope to demonstrate with a trial, to bias your findings. So with your newly gained understanding and this script to refer to eventually, which I'll upload alongside here, you should no longer feel the need to skip the stats section, but you're instead able to put on your Sherlock Holmes hat and to critically investigate. Thank you for your attention, and I hope to enter discussions around this, and I hope you can use this in a beneficial way. If you have any questions or concerns, please do get in touch with me. I'll show you my contact details in a second. Here's also a list of materials that you can start your reading from. There are lots of good websites and trial design groups that I haven't referenced yet. Here are my contact details, and I thank you for your attention. Goodbye.